I'll have to pause these guys for now. All right, so this week we're going to head off into chapter 9, stresses and strains. Resilient. Van Halen's like, I'm not taking any part of it. You could read this chapter. This is an important one. It's not super complicated in the beginning, but it's good to kind of understand the concept of the different stresses. We'll go through it. Let's do the homework first, but there's homework set for today, 2, 3, and 4 out of chapter 9. 6, 10, and 11 will be on Thursday. There's a quiz 2 on Friday, and then there's a makeup quiz 1. So this is a new thing. I've never done this before, but I'm going to offer a makeup every week following the quiz. So, for example, if you got 19 out of 20 on quiz 1 and you really want 20 out of 20, it's not worth the effort, by the way, but I know some of you are going to go down this path. You could take the makeup and try and bust out a better score. But it's really beneficial for folks that didn't get the score they wanted on makeup on quiz 1. So I'm going to try this. It's not too difficult to pull off so far. So you do them both, though. So you don't have to do the makeup, right? That's optional, but quiz 2 is not optional. I built them both. They'll show up on Friday, early in the morning, and they close late at night. Okay. Questions on that? It's kind of new. We'll see how it goes. All right, let's look at the homework. So we'll look at the homework, then we'll look at the quiz, because the makeup's different, so it doesn't matter. And then we'll do stresses. So kind of what we're going to do with homework is I'm going to say things like how to go and do you have questions? Probably not going to work them all the way out. We just don't have the time. But 16 and 17, right? You did these two? Yeah. How'd this one go? Think you got it? So let's talk our way through it. If we're trying to find the inertia about the centroidal. Oh, they want for the cross-section shown, calculate the moment's inertia with respect to both centroidal axes. Yeah, both centroidal axes, but that's okay. Yeah, so XX is going to be in here somewhere, right? And then YY would be here. So for the X, you're going to have to find Y bar. Because the two inertias, the two X inertias are not at the same location, right? This one is down here. This one's up here, the W shape, right? So when we have that situation, we have to find the Y bar, transfer to the Y bar, and go from there. That makes sense? How do we get the inertia of a W shape? Look it up. Absolutely. W150 by 24, we go look it up. How do we get the area of the W shape? Look it up. Yeah. So when you're given a structural shape, that's benefit, right? That's the easy peasy part. How do we know where its Y location is? Like the location of this thing, of the W shape. How do we know where, yeah, half the total distance, how do we know the total height of a W shape? Yeah, is it 150? No, it's going to be something different. Yeah, so you always got to look it up. It's never the nominal. This is called the nominal dimension, or the dimension that we just say. Like when you want a 2x4, you call up and say, I want a 2x4. You don't say, I want a 1.5 by a 3.5. They'd be going, what? What are you talking about? So that's the same kind of thing. So yeah, you got to look this up. You remember what it was? 160. And then if you put your axis down here at the bottom, which is what I would do, then you got to add this 19 to it, right? To get the total Y distance. So it'd be 179 for Y bar. Good? All right. And then what about the plate? How'd you get the inertia of the plate?
The formula for.
Base height cubed over 12. Yep, so just the formula for a rectangle. There's no plates in the back of the book, so. And then what about the y distance to the plates centroid? That's gonna be half of the 19. Yeah, good. So then you got all the parts and pieces. You just have to figure out the transfer distances, which is from here to here for the W, so that's D for the W. Right? And then the transfer distance for the plate is here to here. So you just had to be careful and find those transfer distances. You guys are getting good at it based on the quiz. Like, you have the rhythm of it. You've got it figured out. It's easy to just make little mistakes. So
I didn't realize you could find like inertia in the back of the book, so I had to calculate that. That's what took me.
for the what?
For the I.
Oh,
I
God.
looked up a agent online. That's what
Yeah,
like threw me off, and I was like,
that's brutal.
yeah.
Yeah, no.
So I'm like, oh, you could have just.
Any structural shape, the inertia is in the back.
I found that I had the area, but I didn't realize the.
If you're given a C shape, L shapes are in the back too, but I don't think this one is in the back because it's kind of a custom 3/4 8x6. I would look, but I bet it's not in the back.
It was almost easier for me to do the second one because.
I'm sure it was. You
It
had
was
it
like-
figured out.
Yeah, it's right there.
But that took some time.
Yeah, I mean, it wasn't that bad, but.
I wonder how close you were to their inertia.
I mean,
What's the inertia of a W shape? Anyone have it?
13.4 e to the 6.
How much?
13.4 e to the 6.
I got 13.3.
13,400,000.
I had like.
You got what?
I saw that it was 13,300,000. So
Ooh,
I had like 17, so.
so you're off.
Yeah.
Yeah, but that's because W shapes actually have fillets in the corners, like here and here. There's actually rounds in the real one, so yeah, it would be really hard to actually calculate the inertia. 150 by 24. What's this look?
I just looked up some random, not random, but table online.
Oh,
So I
that's
don't
probably
think
different then.
Yeah, I don't think it's completely, but
What? Is it not in the book?
It's in the book.
I think it's on the very last.
I
think
got
it's-
it from in the book.
Like it's on the back cover.
To calculate it?
Page the way he said.
No. Why doesn't my book have it? I have a 150 by 150. What's happening here?
What page?
495.
Go to 486. That's where the W shape.
Oh, wait. Oh, this is rectangles. Why don't they give you a rectangle at the table? That's weird. Yeah, they don't give you any shape here. All right. Yeah, I was looking at the wrong thing. W shape. It should be the next page, 150. Right, it's the bottom one, yeah. Inertia. 13.4. 10 to the 6 millimeters to the 4.
why are those books different?
That's 13.4 million. Probably a different steel manufacturer.
Yeah, I mean,
So like, if you ever do work with steel, you need to look up the specs for the manufacturer. Like in our area, it's Oregon Steel. Look up that spec there. Don't use this book, right? Because you want their spec. Very good. And then what about this one? This is kind of like we've been doing, right? Where you got to break it into two shapes. You got to calculate your Y bar. Anybody have the Y bar?
2.15.
Anyone get
2.45.
2.45 or 2.1453? Okay. And then it depends on how you broke the shapes up. Right? Because there's one shape here, and then there's one shape here, and you need those distances. So this is like Y1, this is like Y2. It shouldn't be squared, it should be a 2. Right? And then your Y bar And then you just go for transferring. Get the inertia of this one, get the inertia of this one, and then transfer.
You just do the other spot. You do it the other way for X bar, right?
For Y bar, yep, just the exact same thing,
Yeah.
yep. It's definitely less common, but you definitely do it. So this one for Y bar. Any transferring? Like, both of these line up, right? If we look at the Y axis. They're directly in line with the line of symmetry. So when you find the inertia here. And you look up the inertia of this one, you can literally just add them together. Because they're both at the y-axis. Excellent. All right, very good. So that's about what we're gonna do with homework, unless you tell me you need more, like, I don't get this. My homework's terrible. I need to see the solutions, then I'll make a solution video that you can watch. We can walk through it. Like that could be the case with the quiz. Like, I'm gonna go through it, so that'll work for going through it. But if you need more, you just gotta ask for it, right? Okay, let's turn those in.
For example, if I make mistake here and correct right now,
That's perfect. That's what I would do.
because, like, I didn't
That's,
count.
yes, that's how you should do it. Then I'll see that, right? And it
Yeah.
Makes it easier for me to grade, like, I don't really care. I wanna give you all the points. And what I care about is that you learn something from it. You all are the ones that care about points. I don't care about points. So if you need more points back or something for some reason, just let me know.
You said Y bar is 2.4.
Somebody said that. There was another number, like you had 1.5, so I can't confirm that.
Okay.
But I can also, I'll put up the solution that the book has, which is always a little wonky the way they do it. Because they don't really work it out in a lot of detail, but they do always show Y bar and how they got it.
Okay.
So I'll put that up too. Oh, I didn't mean to close there. All right, let's look at the quiz. Which I think if you didn't get your quiz back, it's over there somewhere. 1265 was the number we're looking for. 2 of us nailed it. That's really good. And then like 5 of us were super close, just missed a little detail. So Y bar was 1.8 after going through the AY. So 1.8 to this axis. Y distance to 1, I called the plate 1, was 2.5. Y distance to the rectangle was 1 inch, half of the 2. And then Y bar is 1.8. So between these 3 things, you set up the D distances. Areas, pretty easy to figure out. 8 inches and 7 inches. So to get the inertia of the plate, that's just base height cubed over 12. That was 0.666 inches to the 4th. And then to get the inertia of the rectangle, how do we do that? Back of the book, go see if that shape is there, and it was there. So you could do it in pieces. That was a lot more work. Always go look for the formula. The formula was outside diameter, inside diameter, outside diameter, inside diameter. So these outside, inside dimensions, and it's cubed for this one. So that was in the back of the book. That gave me 3.583 inches to the 4th. So here's your 2 inertias about their own axis, and then we had to transfer.
For the hollow rectangle, I would never do it this way, but technically.
Yep,
Could you break that into 4 rectangles and then just?
you could.
transfer
You
from
could do it
all
that way,
those?
or there was somebody who did it as a big rectangle and then a small rectangle
Oh,
and
mine.
subtract it. Yeah,
Okay.
that works. Is that what you did? Yeah. So Yeah, or 4 solid rectangles. That's a little more that's more transfer, that's for sure, yeah, because you gotta transfer everything, right? So like, yeah, no, don't do that.
That's why I started with, I would never do this.
Right. So then the transfer distances ended up to be 0.7 and 0.8. So that's the difference between the 1/8 and the 2.5 and the 1/8 and the 1. So that's the transfer distances are always the part that can get really sticky. And kind of hard to figure out. So the makeup quiz on Friday, if you want to take it, will be just like the quiz. So it'll be a inertia problem. Not the same, but close. Okay. All right. Very good. Nice job, everybody. There's another one on Friday. So those just keep coming online. You have all day to do it. It's good if you don't use other people to do it and that you just do it yourself. But all good. What else before we go into stress? I think that's pretty much. Did the quiz, we did the homework. Let's talk about chapter 9. Chapter 9 is stresses and strains. Stresses and strains. So let's talk about both stress and strain. Because these two are really fundamental. So when we load anything like this thing, if I load it like this, it's gonna bend, right? If I hang it and then I put a weight on it, it's gonna try and pull it apart. So when I do that, when I'm pulling on it, pulling it apart, but it doesn't break. And I bet I'm putting maybe 10 pounds on right now. So I'm pulling this way with 10 pounds and I'm pulling this way with 10 pounds. Right? Why is it not coming apart? What's resisting that? It's not coming apart. The material, the wood is resisting. All of these fibers, all of them along here are resisting that. If I pulled hard enough, I would just pull it apart. And then those fibers can no longer hold that load. But when I do that, that 10 pounds is transferring all the way through this thing, right? If I try to load it this way with 10 pounds, it doesn't work so well, right? But if I load it with 1 pound, it works. That 1 pound travels all the way through, goes into this table, and then the table carries that 1 pound. And it's strong enough to do it too. Okay. So what we have to figure out is like, okay, this was 5 pounds. This is 10 pounds. This is 20 pounds. This is 30 pounds, right? We have to understand at what point this is no longer going to carry that load. That's stress. The stress in the material is what's carrying the load. The load gets distributed across this cross section. As I pull on it, all the way across, those fibers are loaded. Every little fiber, right? Not so much right near where I grab it. Right near where I grab it, there's some stress concentrations by where you grab it and where you pull on it. But as we move away from my hands, like out here in the middle, it distributes completely across the cross section. And it's called average stress. So the first thing we learn to calculate is average stress, kind of away from the connection points. Like, what's it feel out in here? It might feel something different where my hands are, because my hands are, gripping it, and I'm not gripping the whole cross section. I'm only grabbing the edges, right? So there might be a lot more stress on the edges near where I connect to it. But out here, average stress. So that's the first thing we calculate. And they give us a bunch of, kind of diagrams about that. When we pull on something, that's called tensile stress. When I push down on it, what's that called? Compressive stress. Okay. Sometimes we're given properties for both. Like maybe we can look up tensile stress. maybe we can look up compressive stress. Some materials, they're pretty much the same, so they just give you the yield stress. Okay. So sometimes we can look them up, sometimes we can't. It is the cross section, that area is carrying the load. Not the length of the thing. When I pull on it, it's just the cross section. So that's what we focus on with tensile stress and compressive stress. It's the area perpendicular to the load. My load is here. And here. It's that cross-sectional area, which is perpendicular, right, to the load. Everyone see that?
So that
Huh?
that geometry will determine exactly how much tensile strength.
Yep.
it has.
That's exactly right. So the first thing we do is we learn to calculate it, and it's literally load over area. The book uses sigma for stress. And I will do my best to make a sigma. But your sigma may look different than my sigma. That's okay. It's a Greek letter S, I think. I don't know what the Greek letter is for sigma. And it's load over area. Load is the load you put on something. Area is the cross-sectional area. And this is for tensile and compressive stress. Unfortunately for you, it's called many things. It's not just called tensile stress. It can be called direct stress. It can be called normal stress. Normal meaning 90 degrees. The load is 90 degrees to the area. And it can be called compressive stress and tensile stress. So there's literally 4 names. There's probably even more. Normal stress, direct stress, tensile stress, compressive stress, all the same thing. Why do they do that to us? I don't know. Fortunately, it's just kind of this that they do that to us. Shear stress is just shear stress. It's not got any other names. Okay. So it's load over area. About the easiest, all the stresses we deal with are load over area. It's just the load changes and the area changes. So it's your job to like sort out, oh, this is tensile stress. That's load over cross-sectional area, right? Oh, this is shear stress. That's load over area parallel to the load. So we'll get into that a little bit later. All right, so how do we calculate it? Pretty simple in the beginning. Here's my little object. It's a square, 0.25 by 0.25. I'll let you jot it down. I'm going to give it a length of 40 inches. It's got 2.5 K pulling on it. How much is 2.5 K? 2,500 pounds. Yeah. So a K is a kip. A kip is 1,000 pounds. And it's just our method of making big numbers small. It's like saying ton. What's a ton? 2,000 pounds. Yeah. A kip is 1,000 pounds. Does this look like a compressive stress or a tensile stress? Definitely a tensile stress. Something's trying to pull this thing apart, right? So we know now that sigma, which is stress, is equal to P over A. My method of keeping track of stresses is I wouldn't just write sigma, I would write sigma sub T for tensile stress, because this is a tensile stress, right? If it was compressive, I'd write sigma sub C, compressive stress. No need to have plus and minuses, we're just keeping track of which ones we have. All right. P's the load. What's our load? 2.5 kips. Over the area, cross-sectional area. What's our area? Right here, cross-sectional area, a 1/4 inch by a 1/4 inch, 0.25 inches. It's this area right here, right? It's this area, cross-sectional area. See how the load is 90 degrees from the area perpendicular? That sets up our normal stress, direct stress, tensile stress, all the same thing.
Quick question.
Yeah,
The load,
yep.
how did you get to 2.5?
I just made all this up. Just made it all up. You're gonna have to be given load, cross-sectional area to find stress. If you're not given load, cross-sectional area, then you must be finding either the load or the area. Because you can find any one of these three, right? I can give you, hey, it's this material. So then we can look up the stress. And it's this much area, how much load could it take? So we can work this little formula 3 different ways. But in this problem, I just gave it. It's given. We'll get into the other stuff. This would be what we call an analysis problem. We're analyzing it's something that already exists, right? I even know what it is. It's 836 steel. It's a 1/4 by 1/4, and it's got that load on it. Let's analyze it. Right? We can calculate the tensile stress. Anyone got a number for me?
40 KSI,
How much?
40 KSI.
Others get that? 3.5 divided by a 1/4 times a 1/4.
Yeah.
40 KSI. We would never, the book does this all the time, but we would never calculate a stress without determining something from it. The only reason to calculate a stress is to compare it to something. Okay, so we know the material. It's 836 steel. When you calculate a stress, compare it. Like how much can 836 steel take? Page 499 is the typical average properties of materials.
Big what?
499. The very first one. 836 steel. Okay, and then we get a bunch of properties. We get modulus elasticity, we'll work with that later. We get modulus of rigidity, we will work with that later. We get tensile yield strength at 36 KSI. Tensile yield strength is, and I used to have a rubber band, and you can take a rubber band and stretch it, and that's yielding. It's deforming, not permanently, because you let go of a rubber band, it goes back. So this, when I pull on it, even with 30 pounds, it's deforming. It is stretchy. Believe it or not, I will be able to calculate it. But it is stretching, even with my 10 pounds, it's stretching. When I let go of it, it goes back to its original position. Agreed? That means it's under the yield strength. Yield means permanently deformed. Like even Colton and I holding on to this, pulling on it, we couldn't pull it hard enough to permanently deform. Plus, wood's not that elastic. It really doesn't like to deform. So at some point it's just gonna break. But steel, mild steel, it's phenomenal at deforming. You can pull on it, it stretches, you let go of it, it goes back. Yeah.
In high school, I had a class and we had this machine and it would like pull, is that what that is?
That's what that is.
Show a graph.
Yeah, we're gonna do it. Yeah, absolutely. So here's the deal. When you pull on something, you let go of it. If it goes back, then you are within the yield. You're under the yield. right? If you pull on it, it stretches permanently. You let go of it, it stays stretched. You have exceeded the yield. It's yielded, right?
I don't know if it's necessarily related, but is that kind of like if you put metal inside of liquid nitrogen, it shrinks a little bit?
That's thermal.
Kinda
That's thermal expansion and contraction.
Okay,
We'll do that, but that's a little different. It's a different load that we have to think about, thermal. So this yield strength, that's our upper limit. We actually don't even like to get near the yield because we don't like things to deform, right? We don't want to go across the bridge, it does this, and then when you look at it, it's still down there. Like, that's not good, we don't want that. So yield, we don't get anywhere near really, but it is the number we look at. Like, okay, let's look at the yield for A36, what is it? 36 KSI. What number did we come up with? What happened? It's permanently deformed, yeah. So this is ultimate. That's failure. That means it actually breaks. So again, we don't want to get anywhere near this, and we really don't want to get anywhere near this. But did our little piece of steel break? No, but it did permanently deform, right? It stretched. That's why we love mild steel, because things can stretch quite a bit and not break. And then we can see that it's stretched, and then we can take it out of service or say, hey, that's a problem. We love mild steel for that reason. It has great elasticity. You're not going to think it does, because when you feel it, it's hard as a rock. It's like this thing would never stretch. It stretches phenomenal. That's why we have built our entire world out of mild steel. That's why every bridge you see is rusty, because mild steel doesn't do well in corrosion, right? But we built everything out of it in the beginning. So whenever you calculate a stress, compare it to something. Like this is not good. Right? That is the purpose of calculating stresses, is to compare it to something. Here's a nice little thing about A36 or mild steel. They call it A36. That's because 36 is the yield. 36 KSI. Which is 36,000 PSI, right? 36,000 PSI.
is that for free material?
Hmm?
Is that for like every material? Like if there's like an A40, it would be like.
Oh, no, it's different.
Okay.
Yeah, so I think they give you only a few, and there's so many steels now. There's no way the book would include all of them. But they did include a 992, which is a high strength steel. Notice that its yield is 50. So if our little piece was made out of 992, it would be fine. Would not yield, right? And then they give us a hot rolled at 1020. Even lower than A36. So this is a nice soft steel. It's going to yield at 30,000. And do they give us stainless? Oh, they do. My favorite, stainless. It's at 40 KSI. And then it goes on and on. Like, you can get any alloy you want out of steel. Just go into Oregon Steel Products and look through the laundry list of the different steels you can get. Some are better in corrosion, right? Like a stainless does pretty well out in the environment. It still struggles at the coast, but inland, it does pretty darn well, right? Mild steel, it's horrible. The Newport Bridge, they paint it from one end to the other, and then they go back and paint it again, and then they go back. You can do a whole career as a painter painting the Newport Bridge, because it's going to literally just get painted 2 times a year. It's crazy. I think the San Francisco is the same one. The Golden Gate's the same one. Yeah. Like literally people, that's their whole career, is painting the same bridge. Yeah, sounds terrible to me. But yeah, and then of course we have some other materials that we'll play with, right? I think there's aluminum in here. There's brass, bronze, copper, concrete. There's even titanium, which is super fun to look at. Titanium. Hello. Yeah, 130. So the other number that we really focus in on is this thing, modulus of elasticity. This is an indicator of stretch, ability to kind of be flexible and stretch. We see 29,000 for mild steel and we see 16,500 for titanium. So there's pros and cons to everything, right? Titanium is super strong, but it's got no stretch ability. It's brittle, not fragile, brittle. In other words, you load it, you load it, you load it, it explodes with no indication of failure. It just blows up and it blows up, right? Mild steel, you load it, it stretches, it stretches, it stretches, it stretches. You're loading, stretching, stretching. Then it gets harder, which is really crazy. It has a second life and gets stronger. And next chapter, we explore that phenomenon,
Will temperature affect these as well?
everything. Yep. That's a whole separate analysis. So that's kind of getting to the thing like, is it strong? Well, we have to look at tensile stress. We have to look at compressive stress. We have to look at its ability to deform. We have to look at its ability to resist corrosion and its ability to deal with temperature. All of that is it strong? Depends. So yeah, we'll look at all that. All right, good. Let's do another one. This is a post. It's a 6x6 Doug fir. I'll call it a number 2, but the book doesn't separate that. So wood products are identified as number 1, number 2, and number 3s. Number 3s are really horrible. They're going to have a lot of knots, a lot of holes, not going to be straight, and most places don't even sell it. Number 2s are what you get at Home Depot. Halfway decent, but still can be pretty crappy. And number 1s you have to special order. And those are very nice pieces of wood. So you get a different value for each one. Different tensile stress, different compressive stress, different bending stress. But I don't think the book doesn't differentiate between it. They're just going to say Doug fir.
It's number 1 for like finished work.
Number 1 is for finish work if it's exposed and you want it to look really pretty, or you just want to build with good straight lumber that's dry, because number 1s are dry. Like I built trusses last summer and I ordered number 1s because I needed these things straight. They were going to be exposed and I just didn't want to deal with crappy wood. So yeah, that's the only reason.
Like at the airport, all those, or would that be different?
Probably number 1s. Yeah, if they're exposed. They could be glue lambs too, which is a manufactured lumber. So we'll get into those when we do the lumber set. All right. So just like this one, I gave you the length. Did we use the length? No. So tensile stress, bending stress, compressive stress, length is not a factor. So that's one thing about this class is you kind of, as we move along, you're going to get a lot of information that you don't need. And you just got to be able to choose what you need and what you don't. So I'm going to start that little game pretty early. I'm going to say this is 60 inches long. It's a 6x6, so we know it's cross section, and I'm going to load it with 2 kips. So on my 6x6, 2,000 pounds. A small car, right? I'm pretty sure my Golf is less than 2,000. All right, so, and it's on a piece of concrete, we'll say. Concrete. And we'll make it 2 foot by 2 foot by 6 inches. So a concrete pad. Well, we know our formula. And it's compressive this time. How much is our load? Yeah, 2,000 pounds. And then how much is our area? The structural lumber is in the book, properties of structural lumber. So if you don't know the dimensional drops by heart, which I don't even know, so I always look them up. A 6x6. Here we see 6 by structural, 6x6, 6x8, 6x10, 6x12 is actually 5.5 by 5.5. And its area is 30.3. And they give us inertia when we get to bending stress, we'll need this. So we do get some properties of structural timber. So area 30.3 inches squared. So we have 2,000 or 2.0 kips and 30.3 inches squared. It was 30.3, right? Yeah.
Yeah.
Equals
1,000?
how much? 2,000?
No, 0.066.
Got you.
Point oh 0.066 kips. KSI, sorry. Right?
Yeah.
So-
What?
Huh?
30.3.
30.3.
How'd you get the area?
Back of the book.
5.5 by 5.5. Oh.
Yeah, no, it's 5.5 by 5.5. That should be the same number.
It's 30.2.
Oh, they rounded?
Yeah, they rounded.
Oh.
So cheesy. I hate it when the book does that. It's crap. But honestly, I've worked with a lot of timber. A 6x6 will come to you 5 3/4 by 5 3/4 if it's wet. It'll come to you 5 1/4 by 5 1/4 if it's dry. So really, all that's taken into account in the timber industry. So I'll talk about that in a second when we compare the stress. What do we get? So how many PSI would this be?
Yes.
66 PSI. Right? So 0.066 KSI, kips per square inch, or 66 PSI, pounds per square inch. All right, let's see what the table gives us. What was our wood? Doug fir, that's what we use in this area. We have a lot of Doug fir. Design values for timber construction. And these are the basic design values. They get a lot more complicated than this, but this is what we're going to use. If I can get zoomed in. This is the US units. Down below is the SI units. Doug fir is our first one. And we see that F sub C is compression parallel to grain. Parallel to the grain. So how do we make our posts? Do we make our posts out of the long part of the tree? Yeah, because we don't grow big trees anymore. We can't make them across the tree, right? They're out of the length. So here's the grain. Agreed? Yeah, so are we parallel to the grain or perpendicular to the grain? Parallel to the grain. So that's the first one, compression parallel to grain. 1050 PSI. So you got to watch your tables, they switch. Some tables are KSI, some tables are PSI. 1050. What's ours? 66. How are we?
Good.
We could stack some more cars on this post. It's crazy what wood will carry, like load wise. We don't even use 6x6s for homes, so we use 4x4s. Like, we don't need 6x6s under there. We put several under the home, right? But a standard post and beam foundation is concrete around the house, right? But inside, under the house is this, concrete pads and posts to beams. That's cool. That's it. That's compressive stress and tensile stress, right? These, you'll see there's no like ultimate, there's no compressive or tensile. There is these values. So the second one is perpendicular to the grain. So that loading condition would look like, does this 2K really goes through some other things before it gets to the post, it goes through a beam, typically. Right? So this beam rides on the post. And then the house, the floor joists are crossed here. So all this load comes down and we get 2K maybe coming down perpendicular to the grain on this member. Right? Because the grain of this member is going this way and the load's coming down. That would be perpendicular to the grain. Then it transfers into here and comes down here. Now it's parallel to the grain. Right? So that's how we can get both perpendicular and parallel to the grain. So when we do this beam analysis, we might need to know, hey, make sure it's not crushing, right? All right, so that's what these other ones are for. And these are the limits. We can go right to them. In the wood industry, we can go right to them. They have accounted for yield. They've accounted for everything. These have big factors of safety because wood is organic. It can be wet. It can have knots in it. It's imperfections. It can have a variety of cross sections because some areas are hard, some areas are soft of a tree. So the wood industry takes all that into account and gives us one number, and we can go right to it, like all the way to it without any hesitation. So you can go all the way to 1050 and not even worry about it, right? It's different in the steel industry where we have the yield. We really don't want to get to the yield, so we bring that yield down and kind of adjust that way. But the wood industry does it for us. So that's why when your neighbor is going to come over and say, hey, I want to build a loft, can you size the beam? And you size the beam and say it needs to be an 8 by 14. And your neighbor goes, what the hell? That's huge. I'm not using that. I'm like, whatever, dude. You don't have to, but that's what it should be. I mean, we over design our wood structures big time. You had a question?
I forgot.
That's because I just kept talking.
No.
So if students have questions and I keep talking, they'll forget. All right, good. Let's talk about strain real quick. No, you don't have a homework on it. That's the other part of this chapter. Stresses and strain.
This Thursday's homework, I do have strengths.
Nope. No strain on Thursdays, it's just stress. But what strain is when we put this 2.5 on here, it obviously strains it. That's where the name comes from. But what it does is it stretches it. So this point moves to that point. Agreed? Everything stretches. Titanium stretches. You just end up with a number like to the -8 because it's so tiny. Like there's no stretch. But this actually would be a number that we would understand. Like this could be 20 thousandths or 40 thousandths. Like it is a noticeable stretch. When we pull pieces in that, we will watch them stretch. And then we can let go of it and we'll watch it go back. Right? That's what we can do. This is called deformation. And it's another Greek letter. It's delta, I believe. But it's the amount it's strained. It's amount that it deforms. So strain is deformation. It's a change in size. So what do you think happened? It was 0.25 by 0.25 before we started, right? It was this size. But now we put this 2,500 pounds on it and it stretches. what do you think happens to the cross section?
It shrinks.
Gets smaller. It's got to, doesn't it? We just can't stretch something without shrinking something. So what happens is when we pull on it, this gets bigger and the cross section gets smaller. Agreed? So then what happens to the area if it's no longer 0.25 by 0.25? Let's say it's 0.240 by 0.240. The stress increases because the area goes down. It would have to.
Do you have a relationship? of
Yep,
How much you stress.
Yep.
Versus, yeah.
yep. So stress and strain are like connected. Like there's this very, very common thread between the two, and we use it big time to calculate deformation and everything else, because the stress and the strain is going to be linear. Right? So this is delta strain. So this is deformation. Strain is epsilon. So strain is the relationship between the change and the original. So the original would be 40 inches. So now the length becomes important, because as you pull on something, it's the longer it is, the more opportunity it has to stretch. The shorter it is, the less opportunity it has to stretch. Okay. And so strain is the relationship between the change, delta, and the original length, 40. And it really just gives you the change in length per unit. In other words, this is going to be inches, and this is going to be inches. So our unit is inches, no?
Inches.
It's really unitless, right? Inches above, inches below, but we don't call it unitless. We call it inches per inch. What? Really? Strain gives us the change in length per unit of length. Inches per inch. It's going to change 0.001 inches for every inch. 40 inches, right? That strain is unit per unit, inches per inch. How much it changes per unit length, which is different than the total change. The total change is delta, right? That's this. This is this, and we end up with the change per unit length. It's like, wow, crazy. Why do we do that? Because that's the number we need, is strain. All right. That's a lot, but y'all are pros. Yeah.
How do you, so it's finding delta.
That's a
That's-
different. Yeah,
You have
that's,
to consider the KSI. You have to-
yeah, so we'll have to, in order to get delta, we will have to calculate the strain differently.
Oh,
I'm not going there yet.
yeah.
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 But this relationship between stress and strain is fundamental, and we can use this relationship between stress and strain to get strain, to get it. So we'll know this number, and we'll know the original length, and we'll be able to calculate delta. Which delta is, it's really what we want. Like, hey, how much does this deform? Like, is it going to deform? Is that piston rod going to deform so much in that heat to drive the piston head up into the valve? We don't want that. That'd be bad, right? We don't want your pistons and your valves connecting, though they shouldn't touch. But if it gets overheated, it expands too much, your engine gets too hot, that rod gets too long, and the head reaches the valve, and then we're done.
Or you might want something that like needs to stretch and you're not hitting that.
Exactly. A bridge, for example, the Fremont Bridge, right? When we get 115 degrees, the Fremont Bridge grows approximately 2.5 feet. Yeah. From end to end, 2.5 feet longer. So if that expansion joint in the Fremont is not bigger than 2.5 feet, then we end up with thermal stresses. So there is an expansion joint in the Fremont Bridge and it's over 4 feet. Because 115 is not the temperature we designed to. We designed to like 170, which is like, I don't know, the hottest temperature on the planet or something. Right? But that gives us a lot of expansion in the Fremont Bridge. So yeah, we just gotta know how much things grow and shrink. Same with temperature dropping. When the temperature drops, things shrink. So they can't shrink so much that they fall off the foundation, whatever that is, right? So we have to be able to calc it. All right, nice job, everybody. Your homework, what was it, 2, 3, and 4?
Yeah.
I'm pretty sure they're just stresses. I don't know if you've looked at it. Two is here. 6-inch diameter concrete test cylinders loaded with a compressive force of 113.1 kips. Determine the stress. No problem. You got this. Compare it, please, to concrete. Look it up. It doesn't say to do that, but I'm saying do that. 3, determine the tensile stress in each segment of the, oh, here's the diagram for number 2. So it's here. Determine the tensile stress in each segment of the bar. So with P equals 75. So P 75, P 75. 75 travels throughout the system. It has to, right? So 75 across this cross section, that'll give you a stress. 75 across this cross section, that'll give you a different stress. That makes sense? Okay. And then I think I gave you 4. Is that right?
Yeah.
Calculate the stress developed in the following members that are each subjected to an axial tensile load of 70. Perfect. You're given the material, compare it, please. Look it up and say, oh, that's good. Oh, that's not good. Because that's how we can make this decision on loads and areas. You're set. No deformation there yet. No strain. Love this class. This is like the nuts and bolts of engineering.